Welcome to part B or part two of this podcast on using RQTL to do QTL analyses. What we did in part A is we set up our environment, we loaded our cross data with the appropriate information about how to deal with missing data, what the genotypes were, what the alleles were. We did some diagnostic work in terms of looking to make sure the data set looked relatively clean. And as a beginning programmer or QTL analyst, knowing that you have clean data is going to be pretty hard. We will try to help you identify those places where the data might not be quite so clean and perhaps leave even a little bit about how what you can do with that. Okay, so what we're going to do here in part B is now start looking at what's called a main scan. So what we want to do now is really start looking at the analysis of the chromosomes, and we're looking for what's known as a QTL or multiple QTLs. Okay, so I'm going to start. Remember we still have the data set called Hyper, and we've done some things with Hyper, some calculations, some statistics. So it's not a bad idea to run the program called clean, and this is going to clean out any calculations that have been done on the data set so far, just to make sure any intermediate calculations have been done. It just makes sure that we're sort of nice and clean and ready to go for the next part. All right, this next part's a little confusing. And what you're going to do is you're going to calculate a genotype probability. That's called genoprob. And we're going to do that using the dataset Hyper. We're going to calculate these probabilities in steps of 2.0 centimorgans. So I'm going to put 2.0 there. There's a bunch of settings that you want to set. I'm not going to go into exactly what all of these are here. I am going to use an error probability of, let's see, I'm going to use 1.0 e to the minus 4, so that's 0.0001 error probability. That's a pretty small probability. And what this genotype probability calculation is doing is it's using a statistical technique known as a hidden Markov model, and that's MARKOV, and that's the guy who came up with the statistical technique. And basically, this is basically going to do a probability analysis of the genotypes in your data set. And a guy by the name of Haldane came up with a variation on this algorithm or on this mathematical technique. So we're going to use his variation on here. And as I showed you just a minute ago, we're looking at this in steps of increments of 2 centimorgans. And I'm going to say always do that. So I'm going to say step width equals fixed. There's lots of options here. I would, as beginning QTL programmers, I would recommend just following these settings. So step width of 2, step width being fixed, the end data being 0, error probability being 1 times 10 to the minus 4. These are pretty good numbers for most data sets, so I'd encourage you to stay with them. Okay, so we've done that there. We're now going to, again, build a simulated genotype that we can use to compare some of our data. So we're going to use the sim.geno command. And again, this is going to be one of those things where you can probably follow the settings here. Step 2, again, same idea as before. Okay. Again, as you get more experience in this, you will learn what to do with these settings. Let's see, what do we want? An error probability, once again, equal to 1.0 e to the minus 4. Okay. Same thing here. So again, this is creating, once again, a simulated genotype that we'll use for comparison there. Where am I here? And step width equal fixed. You should not be expected to really understand what all these commands are doing at this point. Just know that these are, so again, we're basically, remember this is all statistical analyses, so we're calculating lots of different kinds of statistics with them, and notice that it takes a minute there to do that. Okay, we are now ready to run our first main scan. We're ready now to do, so you have to do all that stuff. You have to do calc genoprob to do the next part. You don't have to necessarily do the sim.geno, but we typically do, so those are just good things to get into the habits of doing. Okay, I'm going to remind myself what my phenotypes are. Okay, I think I remember blood pressure, sex, and parental grandmother. That's okay. So I'm going to run my first scan now, and I typically call my scans the name of the cross, which is hyper.scan1. Okay, because you're going to use, you might have more than one scan, and so we're going to do a main scan, and the command for that is scan1, and we're doing that on the hyper data set. We're going to do, we only want to do that on phenocolumn equal 1. We want to use a normal modeling mode. And again, some of these commands you won't know. And the method we're going to use here is we're going to use a method here called EM. And again, as you get more experience, you'll learn what these different methods are. There's the EM method, there's the HK method, there's a variety of different methods. And so for now, just go ahead and do that. Okay. So at this point, then, so I've run my scan. We're not ready to do anything with it yet. I also have to do what's called a permutation scan. And again, a lot of these things are going to be, you're going to be wondering what in the world is all this stuff. So as you get more experience, you'll get a little bit more understanding of what these things are. Right now, all you're trying to do is basically get stuff to run so you can generate a map that you can look at and be able to do something with. So we're doing basically the same thing here as we did with the regular scan 1, except here we're going to say we want to run, and this number here, usually we run 1,000 permutations. I'm going to run 100 permutations so it gets done today. So I'm running, if you notice here, I run a scan 1 on the data set looking at column, phenotype column number 1. I run a permutation scan on the same data set on column 1, the blood pressure, and this time I'm saying run some number of permutations. When I hit that, it should now start running, and this will take a minute to go. And you see, that's a good sign if you're getting these messages. That means the scan is running and doing what you want it to do. And there's not much to do other than sit. This is where you go out and get a cup of coffee or a Coke, or go do something else for a few minutes. Again, usually we run these for a lot more than 100 permutations. I'm just doing 100, so it gets done in a reasonable amount of time. A lot of times you'll typically we'll do 1,000, and that takes a pretty long time to run. Okay, so the next thing we want to do is we want to set up some threshold values, and these are values that we'll use to compare our data with. So we're going to do a summary of the scan 1 perm data, and we want to set up a threshold with what's called an alpha threshold value, and we want a number of them. We want it at 37% significance, so that's 0.63. We want it at 90% significance, so that's 0.01, and we want it at 95% significance, so that's 0.05. And you can see there I'm subtracting those numbers from 1. Okay, so we're going to set up these threshold values. If I type in thresh1, I will probably see my lot scores there. So we see we're getting pretty close to 3.0 for our top 5%, and we'll see that graphically in a minute. Okay, what I want to do now is I want to go ahead and plot some of these things. So I'm going to plot scan 1, okay, and I'm going to put a title on it so I know what I'm doing. Okay, main scan plot of BP, and now I should get a main scan plot. There we go. All right. And what should I notice there? Okay, what I should notice there is that I have a pretty big QTL on chromosome 4. Okay, I've got a pretty big chromosome, so there's something in that chart there that's telling me something's happening on chromosome 1 that's really, really having some effect on blood pressure. And that's something I'm going to want to explore a little bit further. Okay, now, okay, that's not a very pretty chart, and so I want to put some thresholds on there. So I'm going to, remember I did 3 thresholds, so threshold 1, okay, bracket, okay, I want, there's threshold, so there's the, oops, threshold 1, bracket 1. So this is going to show me the 37% threshold, and I'm going to say LTY equal dotted, and that's going to, and LWD equal 1, that's the thickness of the line. You'll see what this is going to do in just a minute once I get done typing. Okay, so I put an ab line on there, and notice it put a dotted blue line at the 37% threshold. Okay, I'm going to do the same thing there. I'm going to hit the up arrow there, and I'm going to change that. There's going to be 2, and I'm going to make that a different color. What color do I want to make that? Okay, I'm going to make that green. Okay, I'm going to up arrow and do the 5% threshold, and maybe I'll make this red. Okay, so what I see now is some nice thresholds on there. And again, what I'm looking for there, so here's the 37%, there's the 90%, and there's the 95%. I'm really interested in things that are above 90, probably about above 95%. So, and I'm also looking for lot scores that are above 3, which is about the 95% there. So notice there I got something going on QTL1, I got something going on chromosome 1, I got something going on there on chromosome 4. Everything else there are really below the thresholds, so probably not anything that I care about too much. It's nice to be able to see a summary of all this data. What did I call this thing? Hyperscan 1. Okay, and I can also look at the permutation file. Okay, and I can look at one of the log columns. Let's look at log column equal 1, and let's look at the all the thresholds that are 37% or more. Okay, so we're going to do a summary table, and what you see there is that on chromosomes 1, 2, 4, 5, 6, and 15. Okay, there's some information. Notice where are my big lot scores? Remember, 3 or 4 are my cutoffs. So it looks like at this marker, D1 MT334 on chromosome 1 at centimorgan position 49.2, I've got a pretty interesting lot score, okay, above 3. If I go back to my chart over here, there's chromosome 1. So somewhere on there, there's a marker D1 MT334 that's suggestive of being associated with blood pressure. Certainly on chromosome 4 at location 29.5, that's a huge lot score of 8. And the marker there is D4 MIT 164. Okay, so and I could have gone up here, and I could also say let's look at the 90% ones. Okay, so I'm going to look at the 90% ones. Oops, and get the right value in there. Okay, and notice now that there's only 2. And if I wanted to look at the 95% ones, okay, depending on how fussy you want to be, okay, I still come up with the same 2. Okay, so what this should tell you here is that on chromosome 1 and chromosome 4, around the location 49.2 and around the location 29.5 centimorgans, you've got some serious and significant genetic activity going on that clearly has something to do with high blood pressures. Okay, so I'm going to explore that a little bit further. I'm going to set up something called a marker name, and I'm going to call it marker name 1. And let's see what I want to do there. I want to find the marker in my hyper data set. It's on chromosome equal 1. okay, at position equal, what position was that? What was that? 49.2. Okay, I want to find that marker name there, and let me just go see what it thinks it says. Okay, it tells me exactly what I would expect it to see there. Okay, and what I'm going to do now is what's called an effect plot. Okay, I'm going to do an effect plot. I'm going to do that on my data set. Okay, I'm going to do phenol column equal 1 for blood pressure, and my marker name 1 is going to be equal to the marker name. I could have called it something like Bob, but I didn't. Okay, I'm going to do an effect plot. Okay, we got a new graph here. Okay, all right. What this is showing me here, okay, is I have two genotypes here. I have homozygous dominant and I have heterozygous. Okay, what this is telling me is for this particular marker that the homozygous dominant genotype is really responsible for high blood pressure as compared to the heterozygous one. So notice here the mean here is about, probably that's what, about 103.8 blood pressure. These are my error bars right here, so there's some statistical error in here. And AB is somewhere around 99.8 or so. Okay, so what this is showing me here is that I really have that the AA genotype is the thing that's probably affecting um, the high blood pressure. Likewise, I can do the same thing here. Okay, I can do an effect plot. Where am I here? Oops, I gotta do a new marker. Okay, so I'm gonna do, okay, oops, let me get rid of all of that. Okay, where am I here? Where am I here? Okay, so I'm gonna do marker name number 2. Okay, and again, I'm gonna do a find marker on the hyper data set, okay, on chromosome 4, at position equal to, what was my position? Where is it? Where is it? Where is it? There it is, 29.5. Okay, and now I'm going to do okay, so now I'm going to do an effect plot on hyper, okay, on the blood pressure column, and marker name 1 is equal to marker name 2. Is that what I called it? It is. Okay, and I get a new, okay, and once again, this is also telling me that the AA genotype is primarily responsible for high blood pressure, at least in mice. Okay, so what I'm starting to do now with these markers is start to identify, okay, I know where the gene is, okay, or where I think it is on the chromosome. So clearly something's happening on chromosome 1 and chromosome 4, and this is by way called polygenic, meaning you have more than one gene affecting blood pressure. And what you're seeing here is the AA genotype is probably the thing that's causing this to happen. Okay. At this point, there's lots of things that we can do here. We're going to do one more thing here. We're going to create what's called a confidence interval. Okay, we're going to do a confidence interval, and I'm going to do a confidence interval on chromosome 1, so I'm going to call that confidence interval chromosome 1. Okay, and what we're going to do is we're going to do what's called a Bayesian, that's Bayesnian analysis, statistical analysis of our scan. And I'm going to do scan 1, and I'm doing this on, as you shouldn't be surprised, on chromosome 1, and I'm going to do look at a probability of 0.95%. Okay, so I'm going to run that, and let's take a look and see what that looks like. Okay, so that's done a confidence interval on that. So what I'm going to do now is I'm going to say, go ahead and plot that. Scan 1, chromosome equal 1, LOD column equal 1. And where'd I go there? Where'd I go? Okay, main equal confidence interval for chromosome 1. Looks like it ran off the screen there. Let me get back on the screen there. Okay, and now I get a confidence interval. Okay, again, a sort of a complicated looking chart there. Okay, so let's make this a little bit more more useful. So we're going to say, we're going to take again, that for now, what you want to do is just sort of follow along here and see what we're doing. So I'm going to do, again, you won't understand this particularly. And you'll see after I get this done what we're doing here. Type equal line, that's an L. Let me get this over here so you can see it. Okay, let's make this color equal green, and let's make the thickness of the line equal to 4. All right, let's see what that did for us. Okay, what that's showing us here on chromosome 1 is between about 38 centimorgans and about 85 centimorgans. That's where we're most confident we have some genetic activity that's causing something to do with blood pressure. Okay, and we can do the same thing. Okay, if we want, we can do the same thing with chromosome 4. So we could go and change this to a 4. Okay, make that 4. We could do the same thing again with all of that. Okay, so again, changes from column 1 to column 4. We get that chart. Okay, we can go up here and do that on 4. And then we can go change our lines. Okay. Where'd I go there? Where'd I go? And there's our confidence interval on chromosome 4. Okay, so fundamentally the big thing that you want to be able to do there, let me see if I can go back to this and see if I can find it. So I'm hitting the up arrow to scroll back through. Okay, this is really the chart that you want, and you want to be able to have your, I go back and do my ab lines. There they are. Okay, I want that ab line. Okay, I want this ab line. I want 2. And I want 3. This is really the chart that you want. The other thing that's really particularly useful here is the summary of your scan. Okay. That's a particularly useful data set because what that's telling you there is exactly on chromosome 1, and you should see the QTL there, and exactly on chromosome 4, you can't miss that. At positions 49.2 centimorgans and 29.5 centimorgans, you have significant QTLs. And now what you would do is you would really start exploring those areas of the chromosomes in much more detail to try to actually isolate exactly what gene or genes you are concerned about. Okay, I think that's all we're going to do for this, and good luck on practicing this, and good luck on your own data set that I'm going to have you do. Thanks. Bye.